All right, hey AP Chemist, this is going to be the important information part 2-4. This is going to be the first time I write OMG AP Chem. Please highlight, make a note, because it's going to be the first thing that we are learning that is something that is tested on the AP exam. I have some sample AP style questions, and I'm including it in your summer work this year, and it's going to be great. And so this is average mass of the elements and mass spectra. So if you look on the periodic table, in our previous lecture, we talked about protons and how if I add up, I'll get the mass number, and the mass number is a whole number. But if you really look at our periodic table, and if you want, you could pause this and rotate this. Let's say I'm looking at neon. The mass right here at the bottom, right? If we look at this mass is not a whole number. So this mass is not a whole number. How do you get a decimal from protons and neutrons that are whole numbers, right? How do we get 2110 neon and we go and we have 20.180? Well, cat's out of the bag here. Elements of a certain sample, let's say I had 100 particles. Some of those particles will have a mass of 21. Some of those particles will have a mass of 20, and some of those particles will have a mass of 22. If I do a weighted average of these isotopes, I will get this mass of 20.18. So how do I calculate this? This is going to be our first big equation calculation, right? OMG. And so I'm going to read through it, and then you're going to see examples of me using this. If I want to get this atomic mass, I'm going to call it an average atomic mass. It's the sum, that's what that big, looks like a E, sum of all of the fraction of the isotopes times the mass of the isotope. So, for example, it'll be the fraction or percentage of isotope 1 times the mass of isotope 1 plus the percentage or fraction of isotope 2 times the mass of isotope 2 plus the percentage or fraction, because we know that we could turn percentages into fractions, times the mass of isotope 3. If I take all these multiplications and then I add them together, that will be the average atomic mass. This is kind of like calculating your grade in a class. Like calculating your grade in a class. Right? Like summatives are 70% is like summative, and then 30% is formative, and you have all these points, then you would use those percentages and figure out what your weighted average is for the class. So we're going to apply this to isotopes. So the way that we figure out these masses and these fractions, the way that we figure out how can we get these mass and fractions, actually, of isotopes, we use something called mass spectrometry. And this is OMG big for AP chemistry. You're going to be hearing and using and answering questions about mass spectrometry once in a while in AP chemistry. So masses of atoms and percent abundance of isotopes of elements are measured using mass spectrometry. So basically, here's the little setup here. It's a technique that separates particles according to the mass. Sample of atoms are injected and vaporized. Let's say I have like a sample of neon here. So let's say this is neon. I have a sample of neon. It's put into and injected. Atoms are ionized then. They into positively charged particles. So each atom loses electrons. Loses an electron to become positively charged. Mass spectrometer only reads positive charge. So anything negative, not going to be read in the detector of the mass spectrometer. So we throw the samples in there, they become charged. So now I have like these positively charged particles. Just imagine that these circles with the positive charge are neons with the positive charge. Then they go through the magnets, they bend the particles towards a specific detector, and the detector reads it to a graph. So I'll get a graph, and I'll get different peaks. Each peak is for a different isotope. So if there are 3 peaks, that means I have 3 isotopes. And they'll have different heights, which are different abundances. 3 heights, 3 abundances, or percentages. And so here's an example of neon. Here is a mass spectra of neon, or mass spectrum of neon. On the y-axis, we have the percent abundance, or even the fraction. And then on the x-axis, we have something called m over z. It's a mass to charge ratio that's only positive. So as you can see, this highest one right here is neon with a mass of 20. This is the most abundant, meaning the highest percentage isotope. Then we have neon 21. This looks like it's the least abundant, only being 0.26%. And then finally we have neon 22, which is 8.82%. And so what this percentage really means, remember, percentages are a number over 100. So 90.92% is really 90.92 over 100. That is, if I have 100 particles, 90.92 of them are going to have a mass of 20. So let's use this data here now to calculate the average atomic mass of neon. So remember, the average atomic mass from our previous page is going to be the sum of the fraction or percentage of each isotope times the mass of the isotope. For this graph, we have 3 isotopes. So we're going to have to do this sum 3 times. So let's do the first one. The first isotope would be a neon with the mass of 20. It is 90.92%, which I'll say is 90.92 divided by 100 times 20. And I'm going to use units of something called AMU. AMU are known as atomic mass units. Essentially, they'll be grams later, but we use those in calculations with this percent abundance fun stuff. So I have the percentage or the fraction times the mass. Then I have the next isotope, which is, I'll do 26%. So it'll be 0.26 divided by 100 times 21, AMU, plus 8.82 divided by 100, that's 8.82%, times 22, AMU. If I do all of this math, I'll get 18.184 AMU plus 0.0546 AMU plus 1.9404 AMU. Adding these all together, I will get 20.179 AMU, which is the approximate 20.18 AMU that is found on the periodic table that we saw on the page before. So we just proved that calculation. So this is how you calculate an average atomic mass. You take the percentage, you divide that by 100, and then multiply it by the mass. You could also multiply the percentage by the mass and then divide by 100 later. That will work consistently well if you're okay with the math. Let's do another example. The mass spectrum of an element sample can be used to determine the atomic mass of that sample of the element. For example, consider the mass spectrum of a naturally occurring sample of silver. Right? Silver is Ag. Right here, I have Ag107 and Ag109. That means it's mass of 107, and it's got a mass of 109. Okay? Well, look at this now. This is no longer percentage. This is intensity. Intensity you could use as like our fraction here. But intensity is kind of like number of particles. Okay? Well, if I'm looking at this number here and I could approximate, right, it looks like AG107 is, I don't know, I'll say about 95% intense, and then AG109 is about 100% intense. That is not out of a percentage anymore. That is, I'll just call it intensity units. I could make fractions out of this. I have 100 plus 95 equals 195, excuse me, which becomes my denominator for my fraction. And for AG107, now the fraction is 95 over 195. For AG109, my fraction becomes 100 over 195. These two fractions add up to a total fraction of 1, right? 100 plus 95 is 195 over 1. I could use these fractions still in my math. If I want to get the average atomic mass, I could use these fractions, because again, the calculation is fraction of isotope times the mass of the isotope. So I will do 95 over 195 times 107 plus 100 over 195 times 109. And these are both AMU. I could do this math and I could do these calculations here, and I will get the average atomic mass. You don't need the percentage. This is not typical. I'm going to say it's not typical to use intensity, but we can still do the math here. I'll do 95 divided by 195, and I'll multiply that by 107, and I'll get 52.128 AMU, and I'll add that to 100 divided by 195 times 109, and I'll get 55.897 AMU. If I add these two together, I will get my average atomic mass, which is, it says approximately 111.03 AMU. Now, I didn't have these numbers exactly, but if you had those numbers exactly, this is what the calculation would look like. Does this match on the periodic table? Not exactly. If you look at silver, the approximate molar mass of silver on the periodic table, Ag, is, I'm trying to look for it on my end here. Let me look. For Ag, it is approximately 108. So where are my calculations wrong here? I made up these numbers. But this is how you would be doing the calculation. These numbers should match on the periodic table, and maybe I'm missing other information. Maybe I'm missing other isotopes. But this is how you would get the fraction and multiply times the mass. Let's do another example that goes back to intensity here. And so let's look at this chlorine one. Again, we have intensity. So I'd have to make up my fractions here. So I have 100% 35, and I have a little bit under 100%. Let's say it's about 40. So I have 100 is going to be Cl35, and then I have 40, which are going to be Cl37. Altogether, that's 140. So I have my fractions now. I have 100 over 140 is my mass of 35 AMU. And then I have my 40 over 140 times 37 AMU. That's my mass of 37. And if I do this math all together, I will get my average atomic mass, or whatever's close to it. So I get 100 divided by 140 times 35. And then I add that to 40 divided by 140. Oops, sorry, hold on. 40 divided by 140 times 37. And I add that to 100, which was about 25. I get about 35 35.57 approximately, which is pretty good because on the periodic table it's 35.45. So this is all with my significant figures and rounding. That's what happened there. Okay, so that is how we calculate and do average atomic mass. I'm going to do 2 AP style questions now that require us to know about mass spectra and reading average atomic masses, and then I'm going to leave you to doing some practice with average atomic mass and mass spectrometry. So let's look at our first one. This is an AP exam question. I believe this is from 2016. So here's a mass spectrum. It says the elements I and Ti, that's iodine and tellurium, have similar average atomic masses. A sample that was believed to be a mixture of I and Te was run through a mass spectrometer, resulting in the data above. All of the following statements are true. That's big. So all of these are facts. So none of these are going to be distractors, but you have to know which fact I'm going to use to support which one would be the best basis for concluding that the sample was pure tellurium. So A, Te forms ions with a -2 charge, whereas I forms ions with a negative charge. Remember, mass spectra only does positive charge. So can't be A. B, Te is more abundant than I in the universe. That would be great, but that's not going to help me figure out whether this is Te or I. I mean, there are a lot of isotopes. It would overpower it, but this isn't going to help me answer the question. C, I consists of only one naturally occurring isotope with 74 neutrons. And if that were true, if I look for I on the periodic table, I has an atomic number of 53. 53 plus 74 is going to be the mass number. That's 127. There is nothing at 127. It says I consists of only one naturally occurring isotope with 74 neutrons, whereas Te has more than one isotope. That's a fact, because it says all the statements are true. It's not in this sample. There is no 127. This must be Te. C is the correct answer. And then D says I has a high first ionization energy. That's the energy required to remove an electron. And that is not going to help us with this because energy required to remove an electron is not involved in the masses of these elements. So it's definitely not D either. So the correct answer is C there. Finally, we have another AP style question. I believe this is from the AP Chem 2018 exam. The mass spectrum of an average sample of a pure element is shown in the figure above or left here. Which of the following is the identity of the element? They'll just ask you straight out. Use the mass spectra, get the average atomic mass, then identify the element. So get average atomic mass, and that's going to use the periodic table to identify element. Now, what's nice here is as of 2022 to 2023, you can use calculators on the multiple choice section. In the past, you were not allowed to use calculators on the multiple choice questions. But now, as of this 2022-2023 year, and in the future, you will be allowed to use calculators. So that's great. That makes us not have to worry about making simplified numbers with math. I'll just identify them. So I see that I have 1, 2, 3. I have 4 isotopes. So I have an isotope with a mass of 90, and its percentage is 50. Great. This is percent abundance now, so I don't have to worry about making a separate fraction, otherwise 50 over 100. So I could start by getting, I'm going to say AAM is the average atomic mass. I'll do 50 over 100 times 90. Then I'll do the next one. I have, this looks like it's about 10. So 10 over 100 times 91. Plus, this next one looks like 20. 20 over 100 times 92. Plus, there's no 93. I have 20 over 100 times 94. Luckily, 50, 10, 20, and 20 adds up to 100%. The sum of your percentages should add up to 100%. Side note, if I do all this math, I'll get approximately 90.3 AMU. If I look on the periodic table for 91.3, the element that is closest to a mass of 91.3 is zirconium, Zr, which means the correct answer is B, Zr. All right, that was a long lecture here, but very important calculations. Know how to calculate average atomic mass using the percentage or fraction abundance times the mass. Know how to read a mass spectra, the number of peaks is the number of isotopes, and then be able to answer questions about conceptual ideas about mass spectra and identifying elements. You could identify an element by its mass in the periodic table. Alrighty, use these notes and lectures now to answer exercises 6, 7, 8, and 9 on your own. If you have any questions or concerns, please let me know. Some of them are going to ask you to construct a mass spectra. Remember, number of peaks equals number of isotopes. Remember that. I see that there are 3 peaks here, or 3 isotopes, so I'll have 3 peaks. And then the height is going to be equal to the percentage. So you could easily construct a graph here and then do the calculation.